What? Yeah, this and this are actually the same thing. This is the power of Lindenmayer systems. So F stands for going forward, and plus stands for changing the angle by 60 degrees, and minus stands for changing the angle by minus 60 degrees. So first we do the first, I'll just use this board. The first F is just this. This is F. And then this is the second one. So F forward plus 60 degrees. F plus 60 degrees. F minus 60 degrees, minus 60 degrees again. F plus 60 degrees. F. Sorry, there should be an F on the end. They're real wrong. But this is what you get. You can think of, the way this is taught is think of a turtle. And a turtle has an X, Y, and a theta, a position, and a rotation. So each symbol is interpreted as having some sort of effect on this turtle. So I wrote a program that does exactly this. So let's look at that. The Koch-Lindenmayer system. So I'll just quickly go over the code. So we have turtle X, turtle Y, turtle theta. This is the important thing. This is where the turtle starts. So, and we start with this string F. And so this is F, the first string. And for int I less than depth, I plus plus, this just means do this certain thing depth times. And depth is a variable. So when I click on the screen, depth increases by 1. String, which is F, equals string, like what the string is now, replace everything in that string by the specific thing. Replace F by F plus F minus minus F plus F. And then we interpret it. We give the symbols meaning by this isomorphism, how we interpret it. So for each character in the string, if the character is F, then what we do is we store the previous values and we move forward. And cosine is sine. It's just how we interpret the angle, go forward, times the increment, which is the length that we go forward by. And we add a new line with those x and y values. So this is what F means. And then plus, what it means is just turn the turtle a little bit. Turn the turtle's angle by pi over 3. And likewise with minus. Subtract from the turtle's angle pi over 3. So we can run this and see what it looks like. And I added some more things like mouse listening. So first of all, and it's printing out the strings. So this right here, if you can see it, it says F. So I'm going to click, and it does that. Just the rule that we were talking about. And now the string says F plus F minus minus F plus F. And when it's interpreted, it gives you this picture. So if we click it again, apply the rule, feed it through, we get this. And it prints the string here. So this is the next string. And then we do it again, and the string gets longer. So we can do it again and again and again, and we get the Koch curve, which is this strange curve that has, you know, infinite length, which is pretty wild. Any questions so far? So a Lindenmayer system is very general. Yeah.
Can you go back to the picture?
Do the picture again? Sure. So.
What if you like see it backwards? Is it going to be the same?
What?
Like flip the picture over and see it that way.
If you flip the picture over?
It's like it has a certain shape, but like take the other shape, like you have, you know, the boundaries of the shape, but like take the other, but like
you want to come up in motion and show what you mean? If you were to view this curve as starting from here and going to here,
would it be the same motion?
and it's upside down, it's the exact same thing. Yeah. That's why it's a fractal. There are copies of itself inside of itself, nested infinitely. That's what it means to be fractal. So for example, this whole thing is this right here. This thing is the same as the whole thing. And likewise, a smaller version of what you were saying. If we flip this upside down to here, it's the same thing. Yeah. So yes. Isn't that cool? So here's another Lindenmayer system, which is a bit more confusing, I think. But it's the same idea. It's a rewrite system, Lindenmayer system. So we start with the string A. And then the rule for grammar is A becomes B minus A plus B, and B becomes A plus B minus A. And the string becomes that. And what these things mean is if it's A or B, go forward. And plus, you know, go turn the turtle one way, and minus turn the turtle the other way. And so what we get here, I'll run this and we can see what it looks like. So first we start with this. This is just a line. And we apply the iteration. This is twice, actually, because if you iterate it once, it goes like upside down and off the screen, so I just didn't do it. So this is after 2 iterations. So think carefully about this shape. Yeah. So I'll just iterate it again. And we'll notice that from each one of these lines, this shape is going to grow again. Only in alternating directions. So the original line was here, here, here. So here it grows this way. Here it grows that way. Here that way. It goes that way. There it goes up.
It's like it's interlocked within itself.
Yeah, it is like it's interlocked within itself. So I'll iterate it once more, and from each one of these little lines is going to stem one of those shapes again. And it's approaching the Sierpinski triangle. So we do it again. Come on, do it again. There. So it's just a bunch of little squiggly lines, but it's becoming the Sierpinski triangle. So, yeah.
Say F string, or what string did you use?
For this?
Yeah.
So this string is not F, but it begins with A. It starts with A here, and it applies these rules to it. So this is the printout of what the string is. So first it's A. After 2 iterations, it becomes this. And then every A in this second string, every A here is going to be replaced by this thing. And that's what we get with this one. It just goes off. So, but it's a similar concept. So this is the string. And likewise with the tree. I had a tree example last time. And we can make a Lindenmayer system for a tree. And the string is FBR. So if we look right here, the string is FBR. And the rule is every B becomes this. So we can really think about this and give these things meaning by interpreting them. So F means go forward. B means there's a bud on the end of the branch. And R